there's also one more topic, which is what I'm going to start talking about today. Now, this is the topic of combinatorics. And again, this is a branch of mathematics from which we need a few results when we develop the statistical mechanics. Okay. So combinatorics is a bit of a daunting sounding name, but the idea is very simple. Combinatorics is basically about counting the number of ways of arranging something, the number of ways to arrange something. So I'll give a few examples in this class which will hopefully make this clear. Okay. And in particular, there are 3 results we need. So I'll do as many as I've got time in this class. The most simple, perhaps the most simple example of combinatorics is suppose that I've got a number of balls, say 10 balls, which are numbered 1 to 10. How many ways can I arrange them in a line? Okay. This is the first example, the number of ways to arrange, let's say n, is a number distinguishable balls in a line. So distinguishable just means that you can tell all of the balls apart. So I can tell this ball is number 1, this ball is number 3, this ball is number 7, and so on. So let's just do a very simple example of this. Suppose that n equals 3, so I've got 3 balls, which say are numbered 1 to 3. How many ways can I arrange these balls? Okay. In a line. So I put the balls in a line. Well, first of all, I can do in the normal order. So I can do ball 1, ball 2, and ball 3. Okay. That arranges the balls in the line. But I could also, for example, swap these 2 around. So then I would get ball 1 followed by ball 3, then ball 2. Okay. And I could decide to start with ball 2 instead of ball 1. So I could do ball 2 and then ball 1 and then ball 3. Or I could again swap around ball 2 and ball 3 and ball 1. And then finally, instead, I could decide to start with ball 3. So I could do ball 3, ball 1, and ball 2, or ball 3, ball 2, and ball 1. So if I arrange them in a line, I can do it like this, or this, or this, or this, or this, or this. So you see, for the case of n equals 3, if I have 3 balls, there are 1, 2, 3, 4, 5, 6 ways to arrange them in a line. So for this case, the answer is 6 ways. There are 6 ways of arranging 3 balls in a line, which I've written there. Okay. That's clear, right? So we have to find the general formula, and this one is not too tricky. In general, the number of ways is just equal to the factorial of n. So this is n times m minus 1 times 3 times 2 times 1. This is definition of factorial. So why is it defined like that? So why is it equal to that? You can think about it in the following way. The first thing I have to choose is which ball comes first. Which ball comes first? So I could put ball 1 first, or I could put ball 2 first, or I can put ball 3 first. Right? So the number of choices for the first ball is just equal to n, because I can put any of the balls first. So this is the number of choices for the first ball. Now once I've chosen the first ball, okay, the first ball is going to be ball number 2, let's say. Right? Once I've chosen the first ball, I only have 2 choices for the next ball. Right? If the first ball is ball number 2, the second ball is either number 1 or number 3. So there are only 2 choices left now. So this is m minus 1. This is the number of choices for the second ball. And you see how it goes on, hopefully. For the third ball, we've already used up 2 balls, so we only have n minus 2 choices. And for the next ball, we have m minus 3 choices. Then it goes all the way down, 3 choices, 2 choices. And for the last ball, you don't have any choice. Right? If I've already told you that the first ball is a 2 and the next ball is a 1, then the last ball has to be 3. So there's no choice for this. And so on. So that's why. Okay, so this is an important result. The number of ways of arranging n distinguishable things, they don't have to be balls, obviously. They can be anything I like, as long as I can tell the difference between them. The number of ways of arranging in the line is n factorial. Now the next case is slightly more tricky. Let's suppose that I've got these balls, but they are not all distinguishable. In particular, I'm going to consider the case where there are 2 types of balls. I'm going to suppose that I've got blue balls, and I've also got red balls, like this. And all of the blue balls look the same, so I can't tell the difference. And all of the red balls look the same, so I can't tell the difference. So in this case, I'm going to want to calculate the number of ways to arrange. So I suppose I'm going to have k blue balls. Okay? To arrange k, and these are all indistinguishable. I can't tell the difference between them. Indistinguishable means you can't tell the difference, right? So indistinguishable balls of one color. Okay, so which I'll assume is going to be blue. Again, the fact that it's color, the fact that it's balls doesn't matter. But it's just important that they're indistinguishable. And suppose I've got n minus k balls of a different color. So I'm going to suppose that not half, some of the balls are blue and some of the balls are red. Yeah, and again, this is in a line. Okay, so let's take this case. N is 5 and K is 3. Right? This means that there are 5 balls in total. 3 of them are blue and 2 of them are red. So if I draw it, I've got 3 blue balls like this. Two red balls like this. And I can't tell the difference between the blue balls. Right? They all look the same. And again, the 2 red balls all look the same. So how many ways can we arrange these in a line? Well, I'll just do it first, and then I'll explain the formula. So first of all, for example, I can put all of the blue balls first, and then put the red balls later. So I can do blue, 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 red, red. That's one possible solution. I can also then switch some of these blue and red balls. So another solution is to go blue, blue, red, blue, red. And I could put this blue ball all the way over. blue, blue, red, red, blue. And finally, I can do red, red, blue, blue, blue. And hopefully you'll agree, this is all of them. Right? This is all of the possible ways of arranging three blue balls and 2 red balls in a line. Okay, so for this example, there are 10 ways. Just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So that's the example. What's the general formula? Okay. So the general formula, the number of ways, you may know this already. It's n factorial divided by k factorial times m minus k factorial. Right? So that's the total number of balls factorial divided by the number of blue balls factorial times the number of red balls factorial. So we can check that in our example, we get 5 factorial divided by 3 factorial 2 factorial. Okay. This is 120 divided by 6 times 2, and indeed that is 10. So the formula works for our example, the case of our example. Okay, so it works for our example, but let me explain why is it true. So why does this formula give you the correct answer? Well, the easiest way, I think, to get this result is to start with distinguishable balls. So if we start with the case where all of the balls are distinguishable, then we go back to the first case. Okay, so we start with the distinguishables like this. 1, 2. Okay, let's not do that. 1, in some order. 1, 3, 4, 2, 5. Okay. And we know, in this case, how many ways there are. There are n factorial ways. Right? If they are all distinguishable, then there are n factorial ways. Next, I paint the balls. I get my blue paint and my red paint, and I paint the balls according to their number. Okay. In this case, there are 3 blue balls, so balls number 1 and 2 and 3, I paint blue. And balls number 4 and 5, I paint red. So you paint balls 1, 2, up to k, blue. Okay. So once we've done this, we get blue ball, then number 4, then another blue ball, then number 5, and you see that by doing this, we've lost some of the ways, right? Because now, I started with this, right? 1, 3, 4, 2, 5. But if instead I started with 3, 1, 4, 2, 5, I would get exactly the same result. Right? Because anyway, balls 1 and 3 are both blue. So these would all give me the same. And similarly, I could do 1, 2, 4, 3, 5. I could do 2, 1, 4, 3, 5. I could do 2, 3, 4, 1, 5, and I could do 3, 2, 4, 1, 5. Okay? And all of these would give me the same results, because in each case I just color these 3 balls in blue, right? So these are all the same. Because once I've colored them in blue, I can no longer tell the difference. Now, how many ways are these? Right? How many ways of different numbers are there? Well, this is k factorial. Right? Because the number of blue balls is k, and I can arrange the blue balls in any way I like. So we started out with n factorial ways, but by coloring balls in blue, we've reduced that number by k factorial. Right? So after we've done this, this gives you n factorial divided by k factorial ways. Okay? Because we started out with n factorial, but k factorial of them are all the same. So we get that. And then finally, you can guess the rest, right? You paint the last balls, so you paint the balls k plus 1 up to n as red. So in this case, that means you paint balls 4 and 5 as red. And you see we've reduced this to the case we want. So now this is blue, blue, red. Red. And you see that this now is just an example of the case we considered here. In fact, it's this one as I did it. Okay. And again, we've reduced the number of ways by this process, because before, if I had 4 and 5 this way, or if I had 5 and 4 this way, they were different. Right? So for example, 1, 3, 4, 2, 5, and 1, 3, 5, 2, 4 were different. But now, I've colored these in red, like this, so they're the same. So now these ways are the same, and how many ways? Well, there's the number of red balls. Right? So this is just n minus k factorial. Probably I shouldn't use the exclamation mark here, because it means something mathematical. Okay, so coloring all the balls blue reduces the number of ways by k factorial. Coloring the remaining balls red reduces it by n minus k factorial. So, in conclusion, the number of ways you get here is just n factorial divided by k factorial, n minus k factorial, which is the result that I told you. So that's why. Okay. One very important application of this is to the binomial distribution, which we talked about for the midterm exam. Remember that the binomial distribution was the was the probability that if I do something n times, and I have a certain probability of success, I will be successful k times. So this is, we do n independent trials. So we try something n times, and each time we have a success probability equal to little p. Okay? So we try something n times. Each time we try, the probability that we succeed is P. And you want to know what's the probability that after trying n times, you succeed k times. The probability of k successes, this is the binomial distribution P of k. Okay. Well, if we have k successes, then we must have n minus k failures. So this probability is equal to, what's the chance that you succeed k times? Well, the probability of success is P, and you have to succeed k times. So that gives you that. Then the probability of failure is 1 minus P, and you fail n minus k times. So you get that. But this is multiplied by the number of ways of succeeding and failing. For example, I could succeed, and then fail, or I could succeed and fail and succeed, or I could succeed and fail and so on. This is multiplied by the number of ways of arranging k lots of success, which I'll put as a check, and n minus k lots of fail, which I'll put as an x. Right, so like I say, so for example, suppose I succeed twice, I could do this by succeeding twice and then failing twice, or I could succeed and then fail twice and succeed, or I could fail twice and then succeed twice, and so on. So the number of different ways of getting k success is dependent upon this combinatorics. Okay? And you see that this is exactly the case we've just considered, right? Whether they're blue and red balls or checks and crosses, it doesn't matter. The number of ways of arranging is still the same. So therefore we get pk, 1 minus p, n minus k, times n factorial over k factorial, n minus k factorial. So using this combinatorical result, we can calculate the binomial distribution like this. Okay, and I think we do just have enough time to do the final combinatorial result that I need. And this final one is a little bit different. We now imagine that we have a certain number of balls, and I have to put these into a certain number of boxes. Okay. This is the number of ways to arrange, and I'm going to suppose that I have n balls which are indistinguishable. Okay, let me just write this down. N indistinguishable balls into k distinguishable buckets. So I have a number of balls and a number of buckets, and I just throw a number of balls in each bucket, and I need to know the number of ways of arranging this. So, again, let me draw an example to make it clear. Suppose that I have 3 balls and 3 buckets. So I have 3 buckets like this, and I have 3 balls. Let's make them black to save pen swapping. And how can I arrange them? So for example, I could decide to put 2 balls in the first bucket and 1 ball in the last bucket. Okay. The balls are indistinguishable, so it doesn't matter which ball I put where. But the buckets are distinguishable. That means I can tell that this bucket has 2 and this bucket has 0. How many ways are there? Okay. Well, let's just do it as a table. Bucket 1, bucket 2, bucket 3, like this. Okay, and okay, let me fit it up. So first of all, let's do it in a consistent way, I can decide to put all of the balls into the first bucket. Right? That's one way of doing it. Next, I'll start moving the balls over. So next, I can put 2 balls in the first bucket, 1 ball in the second bucket. Okay, that's another way. So I can put 2 balls in the first bucket and 1 ball in the last bucket. That's this case. Okay. So those, again, hopefully you'll agree, this is all the ways of putting those balls into those buckets. And if you count them, you find that you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So again, in this case, you get 10 ways. You may have realized, as we were doing it, that this problem is very closely related to number 2. Okay. In fact, if I use number 2, I can derive the result for this, case number 3. So all you do is you abstract it. Okay? Get rid of this. I can extract each of these symbolically as I've written it. So if I go across, I have 3 balls, then 2 lines, and then nothing, right? So this first case becomes ball, 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 line, line. Right? So I've just put the balls here. Then in this next one, I get 2 balls, then a line, then a ball, then a line. Okay? So this second case becomes ball, ball, line, ball, line. This next case, I get ball, ball, line, line, ball. So this becomes ball, ball, line, line, ball. Okay. And you can see how it goes on, right? So the next one is ball, line, ball, ball, line, and so on. Can't be bothered to write it. So hopefully you get what I mean. So I'm just abstracting. I look across, and I just read off what I've got. So here I get ball, line, line, ball, ball. Okay. Here I get line, ball, ball, line, ball. So what you've got here is the number of ways of arranging 3 balls and 2 lines. Okay. So that there's an exact equivalence between this and the previous case. The number of ways of arranging 3 balls in 3 buckets is the same as the number of ways of arranging 3 balls and 2 lines. So therefore this problem is the same as the number of ways of arranging n balls, and notice the number of lines is 1 less than the number of buckets. Right? I have 3 buckets, but there are only 2 lines. So this is now k minus 1 lines. And therefore, the number of ways is just therefore, okay, so what's the formula? It's the total number of objects. Well, this is n plus k minus 1 factorial divided by the number of the first type of object, that's balls, which is n factorial, divided by the number of the second type of object, which is lines. So that's k minus 1 factorial.